Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by David Hollenbach, who is a PI here at SETI. He did his undergraduate work at a liberal arts college in Michigan called Hope College, and he got his PhD at Cornell. And he worked at NASA Ames for many years before, in the last year or so, he's come across to work for the SETI Institute. And today he's going to talk to us about his field of interest, which is star formation in dust clouds around exoplanetary systems or around solar systems other than our own, of course. Okay, so, Dave, thanks very much. Take it away.
Oh, it's a pleasure to be here. And actually, I'm working here at SETI for the last year, mostly actually on the evolution of planet-forming disks around young stars with Uma Gorty. But today I'm going to talk on a sort of a side interest, something that I've been interested in for 40 years, which is astrochemistry. So this is not what I'm really doing here, but hopefully I can make it interesting to you. I mean, people, when they hear astrochemistry these days, they think of one word, which is boring. And hopefully I can make it kind of interesting for you. It's been an interest of mine, as I say, for 40 years. And cosmology and, you know, right now, cosmology and planets around young stars are all the current rage, and that's what everybody's excited about. But 40 years ago, actually, astrochemistry was the rage. I mean, it was a lot of the best astronomers were going into astrochemistry. In the 1970s, there was this incredible race to detect molecules in interstellar clouds. And part of the motivation, there's two sort of motivations. One is that it's the molecules that cool the clouds and that allow stars to form, because then they start to gravitationally collapse in these extremely cold clouds. And the other motivation, even back then, was that there was this realization as we started to detect molecules. One of the molecules, we started to detect amino acids in space, and we started to detect building blocks for amino acids in space. And so part of the motivation became sort of astrobiology, even back in 1970. There was this thought that that was really the beginning of the universe producing molecules that got ever more complex and that eventually led to life. I mean, these molecules made in the interstellar medium might be deposited in planetary bodies and may have sort of given a kickstart to the evolution toward life. So but there was a lot of excitement then. I mean, the last speaker, Ben Zuckerman, was really caught up in that whole. He was finding new molecules that seemed like every week or something like this. And we, first started detecting simple molecules and then more and more complicated molecules. I mean, our knowledge was so primitive. I mean, this is going to show how old I was. But what we knew was, and this is a new picture, but there were pictures like this back in the 60s when I was a graduate student. And we knew there were these dark clouds that, these are called Bach globules. This is in an H2 region or an ionized gas region where the ionized gas is glowing. And then these dark clouds of dust would obscure the light, and so you would see these dark clouds of dust. And if you looked at 21 centimeter, which observations of atomic hydrogen, which we had then in the 60s, you'd also see that atomic hydrogen was associated with these clouds. But we did not know that things were molecular. If you look at textbooks, and I just looked at my old textbook that I taught out of in 1970, they'll say things like, well, this interstellar medium is atomic, and that molecules were a trace abundance. I mean, there were people that suspected that these clouds might be molecular hydrogen, but molecular hydrogen didn't emit anything. You couldn't see it. And at that time, the first molecules that were detected were things like CN and CH and OH, which were trace molecules. And so if you calculated their abundances, they were very low. And so the thought was there was not much mass. It was hard to tell how much molecular hydrogen there was. CO wasn't detected until 1970. So that was sort of the state of our knowledge. And then, as I say, once we started detecting molecules, there was a race to see how many we could. So the thing was, as we thought about it theoretically, and this was my thesis actually at Cornell in the late 1960s, if you want to form molecular hydrogen, in space, you do not do it by having two hydrogen atoms in the gas collide together and form a molecule. In fact, you can't form any molecule really in interstellar space by having two atoms come together and form a molecule. And the reason is that if you're going to form a molecule, you've got to lose energy, because there's a binding energy that binds the molecule together. And you've got to lose some energy to make that system bound. And the way you do it in this process is by radiating a photon. So you lose a little energy and then you're bound. But the problem is that the collision time, when you collide two atoms together, they're only touching each other for 10 to the minus 13 seconds. A very incredibly tiny time. And the time it takes to radiate a photon is 10 orders of magnitude larger than that. So if you calculate how long it would take to make molecular hydrogen by this method in a molecular cloud, it's longer than a Hubble time. It's more than the age of the universe. And that's true of other molecules as well. So you can't just have the atoms come together to form a molecule. So how are they made here on the Earth, for example? If we had a box of hydrogen atoms, would it react? And the answer is yes. It would probably be a bomb that would explode. And the reason is that the densities in the atmosphere here are like 10 to the 19th particles per cubic centimeter. And when you have a density like that, a huge density, then you get three-body reactions. You actually have, quite often, what happens is that three of these atoms come together, and then you have another atom which can carry off the excess energy of binding. And so you can get H2 plus this H, which carries away some of that extra binding energy that allows the H2 to form. But this does not happen in an interstellar cloud because the densities are only 10 to the 4. And so this also takes more than a Hubble time to make the molecular hydrogen. So what I showed was, in the thesis, was that basically molecular hydrogen formed, you need a third body to carry away. You need a body, something to carry away some energy so that it's bound. And what I showed is that if they formed on dust grain surfaces, that was sort of like a catalyst, and the dust grain could absorb some of that energy and then allow the H2 to bind. And so the atoms would hit a dust, they would combine on a dust surface, and you'd form the molecular hydrogen on the dust. Now here's a quiz question. Who was one of my thesis advisors? Frank Drake of the SETI Institute was and my radio astronomy teacher, and a person who taught me my first lessons in SETI in 1966. And he taught me in radio astronomy course he taught. And who was a graduate student with me at Cornell? Jill Tarter. So there's connections that I have with SETI that go back to the 60s, actually. So let's get moving then. Maybe I'll use this pointer that I have. So once the H2 forms in interstellar space, that's all you need. Then you can make molecules like crazy. Because once the H2 forms, then you no longer have to worry about these types of reactions, because you'll always have this third body to carry away a reaction. For example, what happens to H2 in the interstellar clouds, first thing that happens is that a cosmic ray ionizes it, and then another H2 molecule can hit it, and you can see that you can get a new molecule, an H3 plus, out of this, because you've got this H that can carry away the binding energy. And so that you can make a new molecule. Once you have a molecule, you can make a new molecule. And in fact, the way the interstellar chemistry works in basics terms, if you look at the oxygen chemistry in the interstellar cloud, in the gas phase, the oxygen atom hits one of these H3 pluses that we've now created, and that forms an OH plus. And then the OH plus reacts with another hydrogen molecule and forms a water plus, an ionized water. And then an H2 reacts with the H2O plus and forms an H3O plus. And then the H3O plus recombines with an electron and forms water molecules. So you've gotten all these molecules now. Once you have H2, you've got everything else. That's the kickstart. And then you get water, and some of the H3O plus recombines to OH, and that will react with O to form O2 and with carbon to form CO. So that's the fundamental astrochemistry of a cloud. And the predictions of the theoretical models were then that because interstellar clouds have more oxygen than carbon, that all the carbon would go into CO, but there would still be oxygen left over because there was more oxygen elementally than carbon. And the leftover oxygen would go into water, O2, and atomic oxygen. So there'd be a fairly high abundance of these three, O, O2, and water. That was the conventional picture, and that's what the theoretical models gave. Okay, but then there were a series of observations, and I was on this team that really conclusively gave a lot of evidence that the water and O2 abundances were extremely low, much lower than the theory predicted. The SWAS, the submillimeter wave astronomy satellite, was launched in 1998, and it flew till 2007. And its main mission was to look for water and O2 in these molecular clouds because they were thought to be abundant. They might be important in cooling and allowing stars to form and so on. And so what SWAS observed was actually 5 transitions here. The red ones are the ones that are ground state transitions, not that that's that important. The main focus was to do the water. There was actually an isotope of water and the main isotope of water and the O2 right here. And it's just because these other lines happen to fall at frequencies very close to the O2 or the water, we also got the carbon 1 and the 13CO. But so we looked, basically the idea was to look for O2 and water in these clouds. And you can see that these transitions, the rotational transitions, are not very high above ground. So that even a cold cloud, you can see there how in temperature units, how high above ground this excited state is that emits this photon. And you can see that they're 20 K, so that even a 10 or 20 Kelvin cloud, which these clouds out there are very cold, would excite these lines. And so, oops. Here's the story of O that I'm going to pose for you. Oxygen's the 3rd most abundant element in the universe. Hydrogen, helium, and then oxygen. Oxygen's 3rd. So abundant molecules with oxygen, such as I said, are important in cooling clouds and therefore important in understanding star formation. And to date, there's been mysteries about the basic astrochemistry of oxygen. These observations by SWAS showed, and I'm going to show them to you, that O2 and water are very low in abundance. So there's the question, why are they so low in abundance when the original theory models predicted they would be quite high in abundance? Where is the elemental O? I mean, here oxygen's the 3rd most abundant element, and we can't seem to figure out where it is in the interstellar medium. And if we can't understand basic oxygen chemistry, oxygen being the 3rd most abundant element, then we can't understand any astrochemistry. So we're really stuck. And this was a mystery that persisted. I mean, 40 years ago, it wasn't really known. This mystery sort of arose over the past couple decades as we started to measure water abundances. But this lack of understanding of where the O was has been this fairly recent mystery that we just wrote this paper on that I had in the first view graph, and which I'm talking to you about today. So again, let's look at the observational and theoretical background. So I gave you the elemental abundances, but these are the observed gas phase abundances in the diffuse interstellar medium of oxygen, 3 × 10⁻⁴ relative to hydrogen. So there's only, for every 3,000 hydrogen atoms, there's 1 oxygen, whereas for every 10,000 oxygen atoms, there's 1 carbon in the gas. So, and as I say, this is the 3rd most abundant element in the gas. So then, these early, as I mentioned, the early models showed that the most of the gas phase oxygen that didn't get locked up in CO would become either atomic oxygen, molecular oxygen, or water in fairly high abundances. These are the predicted abundances relative to hydrogen that in these theoretical papers. But observations by SWAS, the thing that I just mentioned, and a more recent European space telescope, have shown that the average O2 abundance in molecular clouds is less than 3 × 10⁻⁸. The average water abundance that they observe is 10⁻⁸, way down by orders of magnitude from the predictions. So where is the O? So here are these observations. This is a summary of the SWAS observations and the Odin observations. And what I'm plotting here is the abundance of water. Actually, it's the log of the abundance of water. So -8 is 10⁻⁸. And here are a bunch of different clouds, molecular clouds that are forming stars. And you can see that they average around 10⁻⁸ or so in abundance when they detect the water. These were upper limits. Oh no, actually it was detected in diffuse gas, but there was they thought the abundance was up here, but I'll show later that actually it was quite a bit lower, even in diffuse gas. And remember that the predictions for water, for cold clouds, is way up here, whereas the observations are down here. In outflows, shocks produce a lot of water, and that was known, but this was a mystery. Why was there so little water? So the summary here is that now we're going to go to molecular oxygen. SWAS didn't detect any molecular oxygens and set upper limits of 10⁻⁸. 7, I mean. And Odin, the other European telescope, had one tentative detection in Rho Oph where they measured the abundance to be 2 times 10 to the minus 8. So again, very low abundances of molecular oxygen, completely different from the theory. So you might say, well, maybe the oxygen went to water ice. Maybe it froze out as water ice. But the early observations that looked at water, one way you can detect water ice is that you look at a molecular cloud, it's formed a star in its center. The star is surrounded by dust, which then absorbs the starlight, radiates 3 micron dust, photons from the dust, and water absorbs at 3 microns. That's a vibrational transition of water. And so it absorbs there, and you get an absorption by the water ice that you can observe. And you can then measure the abundance of the water ice by looking at how deep that absorption is. And when they did that, they found that the water abundances ice abundances were very low, that you couldn't put this missing oxygen in water ice, according to these observations. So, the summary of this paradox is there's not enough carbon to lock all the oxygen up in CO. So there's extra oxygen. The oxygen not in CO is not in gas phase O2 or water. The observations show that that's true. It's not in the water ice because of these absorption measurements with these embedded sources, or any other ice like CO2 ice. It's not in atomic oxygen because if it were in atomic oxygen, the chemistry is extremely certain that that oxygen would then make O2 and water in the gas phase, the chemistry that I sort of showed you on that view graph. So it's an indirect. They couldn't directly detect the O or measure the atomic O in these clouds, but it was an indirect argument that it couldn't be atomic O. And it's not in CO2 in the gas. Where is the oxygen? So that's the mystery that we're going to solve today. So here were the early theoretical calculations for if you didn't freeze out anything on dust grains. These dust grains in these clouds are very cold. They're like 10 degrees Kelvin. They're extremely cold. And if an atom hits it, it could stick and freeze onto the surface. But if you forgot about freeze out, which all the early theoretical models did, then you get what I was telling you in words, but now you can see an actual result. This is a time-dependent calculation of the abundances of various species. And this is time in log units. So this is 10 to the 4th years, 10 to the 6th years. And what you see, and this is a cloud that they start off this is in computer code, but they do the chemistry in this computer code, and they allow it to run in time, and they start off with atoms. And so they see how long it takes to form molecules. And what you see is that the water abundance starts to rise at about 1,000 years to levels that are at this 10 to the minus 6 level, way above what we observe. And the oxygen starts to rise in a time scale of 10 to the 5th years to abundances where a lot of the oxygen in this case is tied up in O2 and atomic O. But the O2 is way up at 10 to the minus 5 or more, and we observe that the upper limit on O2 is 10 to the minus 8 or something like that. So something's wrong here with this theoretical model, something very basic. So the first thought is that, well, things freeze onto the water ice in these cold clouds. And so here's a model where they put the freeze out. If a water or an oxygen hit a grain, it would freeze onto the grain surface and never come back to the gas. And then sure enough, you get low abundances, but now you get too low. Because this again is a time-dependent calculation. This is 1,000,000 years here. And this is the water abundance. And what happens is that the water just goes to 0. It all freezes out in 10 to the 5th years. There's no water. But we do detect 10 to the minus 8th of water. So that doesn't agree with observations either. So then, and just to give you a little physics of the freeze out, you can very simply calculate what the time it would take for a given species in the gas to freeze out. And that's the time, suppose you're an oxygen atom, for example, or a water molecule. Then you just want to know how long will it take me to collide with a dust grain? Because as soon as I collide, I'm going to stick and freeze. I mean, it's pretty well known that if those guys hit a dust grain, they'll stick and they'll stick on the surface. So all you have to do is calculate the collision rate for you, the oxygen or the water molecule, to hit a dust grain. And that is just the density of the grains times the cross-section of the grains times your velocity with respect to the grains, which is your thermal velocity in the gas. And when you do that, you get a freeze-out time of 10 to the 5th years for a gas density in the cloud of 10 to the 4th, which is sort of the densities of these clouds. So you can see that things will just freeze out. And these clouds last for 1,000,000 or 10,000,000 years. And so when we look at a typical cloud that's 1,000,000 or 10,000,000 years old, everything should have been frozen out. So, well, what's going on? So then Ted Bergen and some of his coworkers had a sort of an interesting idea. They froze out, this is the same model I showed you with no freeze out, but then here's a new model where they froze out the water, but they didn't allow the CO to freeze out. CO doesn't have as high a binding energy when it is stuck to a grain surface. And so maybe they said the grains are warm enough that they just sort of thermally evaporate all the CO, and the CO is going to be left in the gas in this model. And they ran a time-dependent model, and what you see is that the water goes up here. This is, the dashed line is water and the solid line is O2. The water goes up initially, but then of course it starts to freeze out. But it then, after 10 to the 5th years, you can see it sort of stays at an abundance near 10 to the minus 8th. Why is it staying there? It's because there's CO in the gas. And if you have CO in the gas, what happens is that, I'll show you the reactions in the next view graph, but the CO gets destroyed essentially by the cosmic rays, and it produces atomic oxygen. So you can see that this reservoir of CO, which can't freeze out, is producing atomic oxygen, and the atomic oxygen then reacts to form the water. And so you have a kind of a long-lasting reservoir of oxygen in the gas. But eventually what happens is that as the CO is broken up by cosmic rays into oxygen, and then this is forming water, and that's all getting eventually frozen as water ice on the grains. Notice eventually the CO abundance goes down because all the oxygen has been taken out of the CO and frozen as water ice on the grains. And so once that happens, there's no more CO, then the water abundance goes down and the O2 abundance goes down at about 3 million years. And so it starts to go way below observed levels. So it might work, this might work, except that we think that molecular clouds last longer than 3 million years, and it turns out that, as I pointed out in our paper, and actually Ted was on it, he made a little underestimate of how fast this all went, and actually this destruction of CO goes even a little faster because cosmic rays destroy things faster, and so it even goes down sooner than in this plot that he published in 2000. So it looks like this might work, but it doesn't look like a great explanation. So here's this interesting way that the CO turns into water ice. Cosmic rays ionize helium in the gas. A CO plus a helium ion creates a C plus an O plus a helium. The helium just basically, the helium plus gives its charge to the CO, but it also rips it apart, so you got a C plus and an O. Then the oxygen atom the first thing that happens is that it hits a grain, and then on the grain surface it forms water ice and it just freezes out. So this happens, but it takes a long time to destroy all the CO by this helium. This cosmic ray ionization process is very slow. So if you calculate the time scale for the CO to turn into water ice, here it is. It's about 3 million years, and this is the cosmic ray ionization rate of hydrogen or helium, and this is in sort of units of 10 to the minus 17. Actually, the cosmic ray ionization rate is about 4 times 10 to the minus 17, so this time to convert it is about 1 million years. So very rapidly, the CO will go away too. So anyway, so we got a new model, and here's the bottom line of the whole talk today, so you can actually leave after this view graph if you'd like. But our new model is the following. What people had not been doing is looking at the whole structure of the cloud from the surface to its deep interior. Because you had to look at the whole surface, because what people were measuring was the average abundance of water through the whole cloud. That included the surface and the middle part and all the way to the center of the cloud. And the abundance of water changes very dramatically as you go into a cloud to the center. So when we did a model which included the whole structure, and that's what this shows, this is the surface of the cloud over here, and it's as if photons are coming in from this direction, hitting the surface of the cloud. This is the depth into the cloud. You can just think of that as distance into the cloud, and you might think of this being the center of the cloud someplace in here. But instead of distance, this is the column of hydrogen in from the surface that you go. And what happens is that on the surface, there's so much UV photons from the interstellar medium or from nearby star-forming regions that you photodissociate all the water in the gas. The UV photons just destroy the water, and that turns it back into atomic oxygen. The UV photons rip it apart. So there's an FUV photodissociation of the water. Similarly, in this outer region, the FUV clears the water ice. These grains are cold. They still might try to freeze water ice. But the FUV, the FUV is just a far ultraviolet photon. It's an ultraviolet photon. The FUV will actually be absorbed by the grain and actually kick water out. It's called photodesorption, and it'll kick it back out to the gas. So the FUV keeps ice from forming, and it also destroys the water in the gas. And so you'd have a very low abundance. I'm plotting the abundance of water here. So it's very low, and this is 10 to the minus 7. Remember, the observations are somewhere in here for the average through a cloud. So then it rises. It hits a peak where you've got, at this peak is where roughly the grains are covered with water, but the far ultraviolet is photodesorbing the water, and then it does get photodissociated, but now the UV is attenuated by all the dust between the surface of the cloud and this depth into the cloud. And so there's a lower rate of dissociation, and that leads to a higher abundance of water. But then if you go in further, what happens is that the UV is getting weaker and weaker, so it can't keep the water ice off the grain. And so now suddenly all the water goes into water ice and the water abundance plummets. And you get the whole freeze out of the water. So this is what our models show, is that there's an intermediate depth, I have N max here, where you get the peak in the water abundance of about 10 to the minus 7. So that is a kind of a quick summary of the whole thing. Now we'll go through some details. So in our model, first physical thing we put into these theoretical models is that adsorption. That means the sticking of gas particles on the surface of the grain, freezing on the surface, and then desorption processes, things that get the water off the grain, for example, or the other molecules off the grain. So there's adsorption, and that's just the rate of hitting a given grain of a species S is just given by the density of that species S times the cross-section of the grain times the velocity of that species. So there's a certain rate at which they hit the grain. Then there's a rate at which they thermally desorb. It's like sublimation. If the grain's real hot, it'll just thermally, things will just evaporate off the surface. And I won't go into the details of all this, but that rate depends very sensitively on the temperature of the grain. If the grain gets hotter, it desorbs things very rapidly. I'll show you some examples. Then there's photodesorption. And that's the process that I just mentioned, that the UV, when it hits a grain, can kick off molecules that have been adsorbed on the surface. And that rate is just proportional to the flux of UV photons hitting the grain. And then there's a yield, the yields being on the order of 10 to the minus 3. So for every 1,000 photons that hits a grain, one molecule might get desorbed. And these yields have been measured in the laboratory. And you can see that the rate is then proportional to the UV flux. And the local UV flux is attenuated. This AV is the visual extinction, or the depth into the cloud. And so as you go deeper into the cloud, you have fewer and fewer photons that get exponentially absorbed. And so that rate goes down with depth into the cloud. This is this flux sort of on the surface of the cloud. And G0 is a parameter that measures the FUV intensity. And it's normalized so that G0 of 1 is the interstellar value, and G0 of 100 is 100 times the local interstellar value. If you were just sitting out in interstellar space near the sun someplace, not real close to the sun, but in the solar vicinity, you would have a flux like this due to the massive stars that are producing UV photons. Okay. And one of the things that was interesting, and we found that was very important for our model to match everything, is a very recent theoretical study by Anderson where he confirmed this earlier measurement of the yield of water of 10 to the minus 3, but he found that actually about 2 times as much OH comes off. You have a surface that's water, a UV photon is absorbed by the grain, and instead of kicking off a water molecule, it actually destroys the water on the surface and an OH radical comes off. And so you get some OH that's also injected. And then there's cosmic rays that are in interstellar space. They also desorb, and there's a certain rate per, these parameters are basically how many molecules are on the surface of a given grain. And then this is the rate per molecule. And one of the things that the theory has shown on this is all from the standard literature, is that it's a much higher rate by 4 orders of magnitude for CO than for water. So the cosmic rays do a fairly good job of keeping the CO off the grains, but they can't get water off. Okay, so the chemistry that we have in our model is, I've already gone through this in the introduction, this gas phase chemistry, but what we've added in addition is grain surface chemistry. I said that my thesis was to make H2 on the grain surfaces, molecular hydrogen, but it would also make other molecules. And this turns out to be important because what we have to follow is the oxygen atom hitting a grain, and it sticks as water ice. I mean, it's O-ice, I'm sorry, just an atomic oxygen stuck to the surface of the grain. Then that atomic oxygen can desorb. This gamma here is all the desorption mechanisms that I've mentioned. It can be thermal desorption, photodesorption. This is all in the model. And so that can desorb and go back to the O in the gas. But what it also can happen is that a hydrogen atom from the gas can come and hit the grain and stick to the grain and find that O that's stuck to the grain and produce OH stuck to the grain, OH ice. That OH then can either desorb by all these desorption mechanisms, or another H from the gas can hit the grain, react with it, and form water ice on the grain, a water molecule ice. And then that water can desorb, and as I mentioned, the photodesorption actually leads to OH, but the other desorption mechanisms just put the water in the gas. So all this is in the model. And this is just a little schematic of how the water forms on the grain. You have an oxygen atom stuck to the grain. You've got a hydrogen atom that is stuck previously, and probably what would happen is it would first migrate across the surface and form OH. And then this other second guy comes in, and then he moves, and he reacts with the OH to form a water. You get a water molecule on the grain surface, and then the UV photons can desorb that water out into the gas that can be ejected from the grain surface.
How can a UV photon hit the water but not destroy it? I mean, I understand the OH part, but not why the water just...
Right. It's a good question. And in fact, the theory actually shows that twice as much OH comes off because of that very fact. That what tends to happen, the reason the yield is 10 to the minus 3, first of all, is that when a UV photon comes in, it has a wavelength of 1,000 angstroms. And so that means that in general, it penetrates about 100 angstroms into the grain surface and is absorbed way below the surface. And so a lot of the photons are just wasted because they're absorbed way down here, and it just gets absorbed in that. It doesn't kick anything from the surface off. But about 1 in 1,000 are absorbed by the surface molecules. And so that's why you get these yields of 1,000. Probably what happens, the theory is that it does destroy the water. You produce OH on the surface. Some of these OHs do come off, but then some of the OHs stay on the surface and they recombine with an atomic hydrogen and form water, and that energy then kicks it off. But they just measured it in the laboratory to be about a 2-to-1 ratio. The other thing that the model has is a grain size distribution, not too important to remember, but interstellar dust grains have a variety of sizes, and it goes with the size to the number of them at a particular size goes with the size to the minus 3.5 power. We have that in the model, and then the grain cross-section, the total grain cross-section per hydrogen atom is about 2.2 times 10 to the minus 21 square centimeters.
Are the grains evenly distributed in the cloud?
Yeah. He asked if the grains were evenly distributed in the cloud, and the answer is yes, that we're assuming that. Observationally, it does seem like grains and gas are well mixed, and there's not big changes. Although as you go into a cloud, one thing that we didn't include that can happen is that as you go into the cloud, you get more ice, and so that the ice makes the grains bigger, and there can be some coagulation of the dust in the clouds too, and that would tend to make bigger grains and change this distribution somewhat. And that actually, those processes in general tend to increase this rate because it tends to at least not the coagulation, but the icing adds area to the dust, and that makes this freezing out and photodesorption even more efficient. So just to give you an idea of what the timescales are for all these processes that I've mentioned. So the cosmic ray, we've already talked a little bit about this, but the cosmic ray time to get the CO ice off of a grain is about 3 million years, or maybe 1 million years. I'm sorry, that's this bottom one. Let's go back. This is the cosmic ray time to create helium pluses that destroy the CO and turn the CO into oxygen atoms. And that's about on the order of 1 million years if this number is 4 times 10 to the minus 17. The time for an oxygen or a water to hit a grain and freeze out is about 200,000 years. The cosmic ray de-icing time, this is the time for the cosmic rays to get the CO ice off the grains, is on the order of millions of years. So clouds only last, we don't know exactly how long molecular clouds last, but there's been actually some controversy about that. But it's thought to be somewhere between a few million years to maybe 20 million years. And so you can see that these timescales are getting comparable to the time that the molecules spend there. So you might have to do time-dependent chemistry, particularly in the interior, which we do. Now let's look just at, if you're a given grain, so this is, these are characteristic timescales for a given grain. So imagine you're a grain. What's the time for an oxygen atom in the gas to hit you? It's about 2 times 10 to the 5th seconds, which is a few days. So if you're a given, if you're out there in the molecular cloud and you're a grain, it takes a few days and then an oxygen atom will hit you. The hydrogen atom, because they're much more abundant, hits you in a few seconds. Okay, so that's the time you wait for a hydrogen atom to hit. What's the time to photodesorb a given species? That depends on how intense the UV flux is, because the more intense, the faster it'll get you off. But you can see that that's a fairly long time scale, particularly compared with the time for a hydrogen atom to hit. So if an oxygen atom hits a grain, and if it just waits for 6 seconds, a hydrogen atom will hit it, and it will react with it and form an OH. So typically, UV photons don't photodesorb the O. What happens to the O is that it reacts with an H atom and forms an OH before that happens. Except, there's one caveat to that the thermal desorption time, as I mentioned, is very sensitive to temperature. It goes something like this. You have 800 over the temperature of the grain, and these grain temperatures in these clouds are like between 10 and 30 K. And so if you put that into this formula, you find that if the grains are 10 K, the thing sticks for 3 times 10 to the 12 years, much more than a Hubble time. So it just sticks forever. But if you get it up to 20 K, then it desorbs in 10 to the 4 seconds. And if you get it up to 30 K, the oxygen will desorb in 10 to the minus 2 seconds. So if the grains are warm, they'll desorb the oxygen before an H atom hits. The H atom takes 6 seconds to hit. So that kind of gives you an idea of how this, what happens. If the grains get really hot inside these clouds, then the oxygen's not going to form OH, and it's not going to form water ice. It's not going to do anything. It's just going to desorb back to the gas. So here's our model where we calculate the temperature of the grain, we calculate the chemistry with all these reactions and with all the grain reactions and so forth. This is the one that I showed you in the crude cartoon picture, but these are real computer model results now. So first, let me just, don't worry about too much, I'll guide you through this. This is the abundance again in log units, 10 to the minus 8, 10 to the minus 6, 10 to the minus 4 of all these different species. And this is the depth into the cloud. In this case, not measured by column, but by the extinction in the visible. As you go into the cloud, this AV, you're basically extinguished by e to the minus AV, or 1.8 times AV. But this gives you an idea of how deep into the cloud you go. And you can see water's in red, and you can see just what that cartoon showed you, is that you have very low abundance at the surface because it's photodesorbed from the ice, and it's photodissociated in the gas. Then as you go in and the UV is shielded, you don't get as much photodissociation of the water molecule, and it rises. It hits a kind of a plateau at around maybe 2 times 10 to the minus 7. And then eventually as you go in, the water goes down because it's freezing out. And other destruction mechanisms besides photodissociation come in. Same thing happens with O2. And the same thing happens with OH. And so in our model, how do we answer the question of where the oxygen is? Well, it's all atomic oxygen on the surface. This is atomic oxygen. And it's all water ice in the interior. And I'll come back to why the water ice observations misled us. But they did. But this is our model for the oxygen chemistry. Yeah.
And you talk about the dust. Is this dust silicon dust or carbon dust? Or
it doesn't matter because what really matters is the surface area is the main thing. Now, it's true that the different species like silicate dust versus the carbon dust might have different binding energies of the things to the surface. And so, but those binding energies don't tend to be that important in this, because what tends to happen is that no matter what the binding energy is, well, except it's somewhat important. The number we use for the oxygen is valid, is a very weak binding, and which is why at 30 K the dust will no longer keep the oxygen frozen on long enough to make water. But so that binding energy does come in, but it's really the surface area that's the main problem.
I'm still worried about the abundance. He says carbon is, I guess, fourth. It's less than oxygen.
Right.
And so there's not enough carbon, and silicon is even less than carbon.
Right.
So how is there enough carbon and silicon dust to provide a surface area to deal with all this water? Because the surface area would have less mass than the dust grain.
Right. Well, the water builds up many layers on the surface. It's not just a single, when the water starts to freeze out, In fact,
It's just a nucleus.
in fact, this is what happens here is that this is when a monolayer forms of the water ice. This is the abundance of water ice. And this is when a monolayer forms, and then very rapidly you start forming many, many layers until you get all the oxygen.
The dust is just a nucleus before.
Exactly. It's just a nucleus to freeze things out on.
Effectively, after a period of time, you just have ice grains in the cloud. I mean, you know, it's
Well, yeah,
the dust is covered by ice, and that's really the important surface.
it's the surface, right, in the cloud. Although, realize that there's a fair fraction of the elemental carbon that does go into carbon dust, and there's a fair fraction of the oxygen that goes into silicates. So even if you freeze out all the gas phase oxygen as water, the mass of that compared with the mass in the grains is not that different. Because you do have a fair amount of oxygen and carbon in the dust, and there's quite a bit of mass. The dust is about 1% of the mass of the hydrogen. And this is just the refractory cores, and then if you put the ice on it, it's a little bit more, like 2 times 10, like 2%. So I'm only going to show you that one particular result. You know, we had zillions of results, but I gave this talk once before, and I got so involved in showing this model, that model, and so forth, that my talk lasted way too long. So I'm just showing this one result. It's for a standard density in an interstellar cloud, and it's for a somewhat elevated field because these molecular clouds tend to have O and B stars near them that formed in them, and that tend to give a more elevated field. But it turns out that these results are independent of density and G0, and the UV flux, which is sort of surprising. You think, well, if you increase the UV flux, you should get less water or something in the gas. But what happens is that if you increase the UV flux, this peak just moves into the cloud more. It's the same peak, same abundance, but it just moves in. If you decrease the UV flux, it gets closer to the surface. And I'll show you some equations that will explain why that is. So the depth where you get water ice does depend on the field. As you get higher fields, the water ice doesn't form until deeper into the cloud. And if you get weaker fields, the water ice forms closer to the surface. And that this plateau of water doesn't change with these parameters. So. And here's just to give you an idea what the temperature is as a function of depth into the cloud. Here's the gas temperature, which goes from like 100 degrees, maybe 200 degrees at the surface, and then you can see it dropping and getting pretty close to the dust temperature in the interior, where in the interior it's maybe the dust is maybe 15 degrees or something like that, Kelvin, for this particular case. So here's the, and I know that equations, just people go glassy-eyed, but I just want to show you why things are dependent on some parameters and not others. So if you calculate the abundance of water, basically the equation that you use is that the production of water in the gas is equal to the destruction of water in the gas, because you reach steady state. The production is the UV photons that are, with a certain yield, are liberating the ice from the dust and putting it into the gas. That's the dominant way you get the water into the gas, is from photodesorbing. So that's the rate at which, per cubic centimeter, that you're producing water in the grains. And then the rate you destroy them is that you destroy them by UV photons. And so the UV photons, then you product the flux times a rate. This is a rate for a G0 of 1. And then you have an attenuation of the UV field. And then it's times the density of the water. That gives you the rate at which the water is destroyed per cubic centimeter. And if you equate those two, you get this equation that the abundance of water, there's a density on this side and a density on this side. So the density sort of cancels out. There's a UV field that produces it, but there's a UV field that destroys it. So the UV field dependence cancels out. So when you get the abundance of water, notice that there's not a density in this. There's not a UV field. All it depends on is the yield and how much cross-sectional area you have in grains. And that's it. And so it's very independent, very robust, this answer. Then you have the freeze-out depth. How deep do you get water ice in a cloud? And what you then do is you say, well, this is the rate at which you produce water ice on a surface. It's a collision rate of oxygen atoms in the gas times their velocity. This is a rate per cubic centimeter, and this is the rate at which you photodesorb the water ice, and then there's some equilibrium, and this is the fraction of the surface that's covered by water ice. And so basically, once that becomes unity, that the whole surface is covered with water ice, you basically ice out very rapidly. So if you just set F equal 1, you can get an equation for the AV, the visual depth, optical depth, at which you get freeze out, and it's just logarithmically dependent on the ratio of the UV field divided by the density. So as you increase the UV field, the depth goes in, and it sort of makes sense. So I just wanted to spend one more minute on the theory, and then we'll go into applying it to actual observations. And that is that we did time-dependent chemistry in the interior of the cloud, and something really amazing happens, which astrobiologists would probably be interested in. And that is that this is AV into the cloud. This is at a time-dependent model. This is a snapshot at 2 million years. And these were 5 different models with different densities and different UV fields. And what we've plotted is the carbon over oxygen ratio, elemental ratio, no matter what molecule it's in. We just want to know how many carbons there are in the gas and how many oxygens there are. And that's the ratio of it in the gas. And you start off, as I said, there's less carbon than oxygen in the gas. That's one of the things I was telling you, because we see that in diffuse cloud and so forth. And so you start off with it down here at a ratio of about 0.3 or something, whatever, 0.4. So there's less carbon than oxygen. But as time goes on, you see this one model, this blue model, which is this sort of dense one. The carbon to oxygen ratio gets greater than 1. When that happens, all hell breaks loose in the chemistry. Because as long as there's more oxygen than carbon, then all the carbon's tied up in CO, and you're not going to make any organic molecules. But once carbon gets greater than oxygen in the gas, then you can make C2H2, you can make methane, you can make these long-chain carbon molecules. Lots of things happen, and that has been seen in some clouds, that they look and they go, wow, we see these clouds which have all these carbonaceous molecules in it, not just CO. So it's always been kind of a mystery as well why those clouds, have all these carbonaceous molecules, and here's something that will do it. The only problem in this at 2 million years is that it's true that carbon is greater than oxygen, but here is the actual carbon abundance at that time in the blue, and you can see it's extremely low. So in this model, it's true that carbon is greater than oxygen in the gas, but most of the carbon is frozen out onto the grain in form of methane and other carbon molecules on the grain. So it doesn't really change the gas phase chemistry all that much, because it's such a trace species that you'll produce a little bit of organic stuff, but not very much. But if you wait a little longer, say to 20 million years, which is sort of the upper limit for the lifetime of molecular clouds, then you can see that all these models are getting carbon greater than oxygen, because what's happening is that the water, and all the oxygen is freezing out as water. And even the CO is being broken down by cosmic rays, and that oxygen is going into water, and it leaves carbon in the gas. You got more carbon than oxygen in the gas. All these models have it, and some of these models, now the red one never did, so forget this red, but these models, you can see, some of them have fairly substantial abundances of carbon in the gas, 10 to the minus 6, 10 to the minus 7. So if we wait long enough with time-dependent chemistry, we can get all sorts of organic chemistry going on in these clouds. So to conclude, I just wanted to run through a few applications of this. I mean, this is all fine, it's all theory. Does this agree with observations or not? That's a true test. So first of all, we looked at diffuse clouds in the interstellar medium. These are clouds that don't have too much dust extinction in them. They tend to be kind of atomic because the UV is destroying the molecules. They've been absorbed, but you can see them often in absorption. You have a source behind it which shines light through it, and you see various molecules in absorption. So there's been 3 that have been very well studied. They look toward SAGB2, which is a source of submillimeter continuum, and W49 and W51, and you see the water and the OH in absorption. And from that, you can get a column density of water that you see. And you can get a column density of OH. And there's also ancillary observations of these diffuse clouds in atomic carbon and in CO. And these clouds, typically, these diffuse clouds have an extinction through them of 1 to 5 AV, and are expected to have kind of interstellar radiation fields shining on them. Their densities tend to be about 100. So we looked at these observations on these 3 sources, and the observations were all pretty similar along all 3 lines of sight. You got a water column density of about 10 to the 13, or a few times 10 to the 13. Your OH column is about 3 or 4 times the water column. Your CO column is about 2 times 10 to the 16. And then what the observers do is that to estimate H2 columns, they multiply by 10 to the 4th, because they think that CO to H2 ratios are always 10 to the 4th. So that was just sort of a question mark there, because that's what the observers did. And that's, in fact, when they measured the water abundance, they used this very low column of H2 and ratioed the water to it, and they got a fairly high abundance of water in the diffuse clouds. The way we explain this relatively high abundance of water in the diffuse clouds relative to molecular clouds is that this is what happens. In our model, we have this cloud, AV of 4, G0 of 1, density of 100, very typical diffuse cloud. Our model gives 3 times 10 to the 13 in the water. It does give 3.5 times column, just like observations of OH. That's if we use this new result that the OH is being desorbed from the grains twice as fast as water. And it produces the CO that they observe. But we can actually in our models see what the column of H2 is, and it's 3 times 10 to the 21, not 2 times 10 to the 20. And so that means that the CO ratio is much less. The CO ratio to H2 is much less than 10 to the minus 4. It's 10 to the minus 5. Why is that? It's because we've actually detected then in this cloud what we call missing H2 or dark H2. What it is, it's that there's molecular hydrogen, but where the molecular hydrogen is, it's C+, not CO. And so there's all this molecular hydrogen there where there's not CO. It's where it self-shields itself, and that's the story.
So there's C+ because the oxygen abundance has fallen so low, it's not enough oxygen to make CO?
No, it's C+ because there's enough UV photons. This does not have much extinction, that the UV photons destroy the CO and turns it into atomic carbon, and then the atomic carbon gets ionized by these FUV photons into C+. But the H2 has the ability to self-shield itself from the FUV, and so it's more robust in an FUV field. So we get these regions with H2, but not CO. And they've sort of been rumored in the past, but this may be one of the, a real observation of them. Then there's this, people have looked at what depth into a cloud do we form ice? And this is a paper by Whitted et al. And what they did is they measured the ice. This is the optical depth in the ice at 3 microns. It's absorbing at 3 microns. But this was where they looked in a case where they had a background source looking through torus, so it wasn't an embedded source. And what they found is that you got these linear correlation. There was a lot of ice. But if you extrapolated this down, this is the AV thickness of the layer that you're looking through. If you extrapolated it down, when you got to AV of about 3.2, you didn't have any ice. And that meant that you had to have this certain column of AV of 3.2 before the water ice started to freeze out. And that's on both sides of the cloud because they're looking at sources behind the cloud that go through the back and the front. And what our model shows is that for a typical G0 of 1 and density of 1,000 for torus here, we get a 1.9 AV on one side and 3.8 on both sides. So the 3.8 compared with 3.2 is not bad agreement. And so that explains why there's this threshold column that you need before the water ice starts to freeze out. Then it's too bad we didn't do this theory before SOAS or even during the first few years of SOAS, because this theory we finally developed pretty much after SOAS had ended. Because one of our great ideas with the SOAS telescope was to look at B68. Why B68? It's because it's a nearby cloud, dark cloud, and it has a known density and temperature structure. There's been all these maps of extinction, dust continuum, CO maps. So we knew exactly what the density profile was. We knew exactly what the UV field was shining on. I mean, we had all the parameters fixed. And so we thought, well, if we can observe it, that's a real test of the model. But at that time, we didn't have this model to predict what the abundances were. So we integrated for hundreds of hours with SOAS, desperately trying to detect water and O2, and we only set these very low upper limits, but you can see the model gives 100 times less than that. If we'd have known how little there was, we probably never would have spent hundreds and hundreds of hours integrating on B68. But it agrees, so the model agrees with B68 by a long shot. Then here's a dense cloud, molecular cloud, but it's illuminated by a pretty high field. It's a star-forming cloud in Orion. It's dense, 10 to the 5th. It has a UV field of 10 to the 4th. And so the dust grains are pretty warm, and you got a really high field at the surface. And the observations, this is now intensity units, ergs per square centimeter per second per steradian. These are the observations. This is not abundances. This is intensity now. In the observation, they did detect the water. They didn't detect the O2. These are the model results using just the standard UV field and density that people quote is perfect agreement with water, and our O2 is definitely lower than what the upper limit was. Then there's Rho-OF. This is a nice case because the molecular oxygen has been seen in Rho-OF. And so there's lots of observations that it's on the 450 micron peak in Rho-OF, where the density is about 10 to the 5. The outside UV field shining on this cloud is about 300. And the observations, these are intensity units again. The observations were 10 to the minus 7. Our model gives 10 to the minus 7. The O2 at this transition, which is the SWAS transition, was SWAS had an upper limit of 2 times 10 to the minus 8. We get 2 times 10 to the minus 9 in the model. But Odin looked at a different O2 transition and measured a column density. That was what they quoted in their paper. We didn't have that transition in our model, so we didn't have it in ergs per square centimeter. But they quoted a column, and our column of water, of O2, is agreed with theirs. So perfect agreement of the O2 and the water in this particular cloud. So it really does well, explains everything, and now I'm just going to summarize what we've done. So we modeled the structure of molecular clouds, densities, and we have a huge range of models, huge range of UV fields shining on them. The basic structure is that the surface is photodissociated. There aren't any molecules because they photodissociate. There's a middle region where the ices are photodesorbed, and you get fairly high abundances of the molecules, but not too high. And then you have a freeze-out region where all the molecules freeze on the grains, and there's just nothing in terms of the molecules in the gas. And the freeze-out layer needs time-dependent chemistry because the time scales for the reach steady state are quite long. We can get these C to O ratios greater than 1 in the freeze-out layer due to the freeze-out of much of the oxygen into water ice. And how do we answer the question that I posed, the paradox that was facing, and where people were making various ideas? For what we said, as I showed you, is that for AV less than this sort of freeze-out depth, the oxygen that's not in CO is in atomic O. And for AV greater than the freeze-out depth, the oxygen not in CO is in water ice. That's our answer to where the oxygen is. And in fact, in our standard model, if you go to an AV of 10, which is the typical depth into a molecular cloud, through a cloud, 50% is water ice, 25% atomic oxygen, 10% CO ice, 8% CO. That's where the oxygen is. So a lot in water ice, quite a bit in atomic oxygen on the surfaces, and then there's some oxygen tied up in gas phase CO and ice CO. So what about those? I told you, I fooled you, see, because I said, well, the observations are saying it wasn't in water ice, and here you're putting it all in water ice. You tricked me. And the answer is that they were using embedded sources to find the water. Now, when you have an embedded source inside a molecular cloud, most of the column, because the density tends to be highest right around the source, and then it gets lower as you go away from the source, most of the column density is right near the source. Right near the source, it's an infrared source. It's heating up the dust grains. Right near the source, the dust is so warm that you produce that the ice doesn't form. You produce gas phase. It just all evaporates because the dust is so warm. It just thermally evaporates all the ice surface off. So what they were seeing was that there wasn't much water ice, but that's because a lot of their column was in there where it was too warm for the water ice to form. They weren't really probing the cold molecular cloud. It's only later, with Spitzer and more recent observations, that we've actually used background sources that were not embedded, that just the line of sight went right through the cold cloud. And now we do see that the water ice abundance is high, and probably all the oxygen is in water ice, or much of it. So, and the other conclusion is that the water, they peak in abundance at around 10 to the minus 7, independent of these parameters in this sort of intermediate zone, the photodesorption layer. The columns are about 10 to the 15, which is what is observed. The models match all these observations, and we can predict for Herschel's this new telescope that the Europeans, with a NASA minor partner, has just launched and is operating. We can look for O2 and water, and we make predictions for some of these Herschel observations. So the final view graph is that Bergen, in his paper in 2000, said, if you have a good astrochemical model, it has to obey these following tests. And so one is a low abundance of O2, a low abundance of water, an explanation for the higher abundance of water in diffuse clouds, which I sort of try to give you, a column density ice abundance of around 10 to the minus 4, and the existence of complex carbon-bearing species in the gas phase in some regions. And so ours explains all 5, so it passes the test. So thank you very much. Yeah.
Thanks very much, Dave.
Sure.
I'll ask the first question. Just hold for a second.
Okay.
So, are you able to? Are there extended enough sources behind extended enough clouds to view the same cloud, but with different optical depths out to the edges, so you can see areas where you don't have high enough AV to have water ice and so on? So you can see a map of the ice within the cloud by
Yeah.
looking at different optical depths through the edges of the cloud?
No, all you can do is a lot of these ice observations are sort of in where these molecules that freeze on surfaces, they have vibrational transitions. That's where they absorb. They sort of vibrate, and those tend to be somewhere between 3 microns and 12 microns. It's that region. So you need a bright background source that's at 10 microns, and it's just like if you look at an H2 region, there is some of that, but it's just too weak. You know, what they usually have to use is some bright point source that's, you know, some star-forming region in the background or something that you can get a nice bright beam through the cloud.
Thanks. 2 questions, David. The first one is sort of a little bit of follow-up on what he's saying. In other words, if you were to map in the submillimeter waves of water, you should see a profile that is different in your model from one where the water goes monotonically, either coming out or coming in. But the other question I was
You
having...
mean it'd be sort of limb brightened because there'll
Yeah,
be this
because you
region
have
where
a
it
peak.
peaks?
Yeah.
So if you map across it, yeah,
Yeah.
we've been thinking about that.
But
And,
you didn't, neither SWAS nor Roll didn't try that, in other words, I guess.
No, it hasn't really been done, although, you know, SWAS did map the water in Orion, for example. And the answer is that it didn't see much limb brightening. So you've made a good question because, you know, but to produce this limb brightening, you have to have a very homogeneous cloud, if you see what I mean.
Fair enough.
That it has to be a very homogeneous density. If it's clumpy, then in some lines of sight, where it turns water will be deeper than in other lines of sight because the peak happens at a certain AV or a certain column, but in some lines of sight, there'll be holes and so forth so that the column won't get up to that critical column until you're much deeper into the cloud in terms of position.
That's fair
And so
enough.
that smears it. The other answer is that the other thing about it is that this water transition actually does scatter. The water photons scatter from each other. And so you get some scattering that blurs things too. It's not like you're just seeing it from the point of origin, that the photons can go and then they can be scattered. And so that blurs things. So we think those are the explanations of why we don't see this limb brightening. But it's a very good point.
Okay, so second
And you would see it if we can get sensitivity to see molecular oxygen, which doesn't scatter, then you know, maybe there'll be a little bit more limb brightening, but we
you'll
don't have
probably
much
be able to see it in
observations.
water if you have good enough spectral resolution as well. But the second question I was having is looking at Doug Whittett's data, and you know, you showed the torus sample, but he's done it in a couple of other clouds as well. And I guess there are some of those background sources are embedded, but there certainly are true background sources in his sample as well.
Mm-hmm.
So would you actually expect to see that good a linear correlation as you're seeing both in Taurus and let's say in Chameleon as well, if you were looking at true background sources and again this kind of distribution for where the water ice would be?
I'm not sure I understand the question because certainly, like in this torus, he's got a lot of different lines of sights through torus, and these are just the AV on those lines of sight, you know, from the front of the cloud to the back of the cloud. And so some of those lines of sight went through, you know, very little column, some went through a lot of column. And so then he just plotted the depth of the water. I mean, so he's probing all these different regions. And in our model, I mean, it takes a certain depth into the cloud before you turn into water ice so that we do predict what this threshold is. And then once you get more than that threshold, then everything in excess of 3.2 is pretty much water, you know what I mean? So that's why you'd get a linear line that would then intersect at this. So I think it works pretty well for the torus observations. And there have been some more observations where, for example, our prediction is that if you have a source that has a higher G0, then this threshold will be deeper in. It only goes logarithmically, but it does get bigger. And there's some tentative observational results now that is indeed the case, that when we look at clouds that have like Rho Oph has a higher G0 on the molecular part of the cloud, and it looks like the threshold might be deeper in, like our model predicts.
Hi, Dave. My question regarding the adsorption-desorption model
Yeah.
with interaction of the molecules with the grains. It seems that in these cold regions, as we mentioned before, the grain is just the nucleus of a big ice particle. Now, is it important that the surface area of the ice is important rather than the surface area of the grain as it goes?
Right.
And that changes with time.
Right.
Would that be a factor?
Yeah.
Change things?
In fact, it's a good thing. We actually, when Michael Kaufman and I originally did our model, we actually included that, but it turned out that we needed to compare it with. We wanted to link our code, which is a steady state code at the surface, with Ted Bergen's code, which was a time-dependent code in the interior. And he didn't have it, and he didn't have the time to put that effect in. So we eventually didn't put that effect in. But we did find that as you form the ice, as you say, the area gets bigger, and that actually accelerates, because the cross-sectional area gets bigger, it accelerates the freezing out of things, because you now have more area. And it can be a factor of a few. I mean, it can accelerate things by a factor of a few. And in a sense, what you can do, I don't know if you saw, but there was this plot that I had. I can quickly get it. I'm going the wrong way, sorry. Of the equations. And this shows you how the abundance of water in the gas phase is tied to the area of the grain. So if the area of the grain goes up, you will get bigger abundances of water. And so if you get an extra area of a factor of 2 or 3, you'll get higher abundances of the water caused by that.
Dave, my question is along the similar lines, and it concerns the adsorption. It seemed like your equation for adsorption of things on grains was purely mechanistic and assumed a probability of 1.
It did.
But it's my understanding from lab work that they do, say, in Alomandola and Sanford's labs, that the probability is not 1, and it's species dependent. And this, if true, is something that would seem to slow down the freeze out, or at least alter that portion of the equation.
Right.
You apparently aren't taking anything like that into account.
No. This is only based on my own theoretical work, but I think that sticking coefficient, it might be as low as 1/3, but it's high. But you have to realize, I don't know at what temperature Lou is working at for this bouncing, but if you're in an interstellar cloud and the temperature is only 20 K, the atoms are moving pretty slowly. And then if they approach a surface, they start to feel the surface potential, which binds them. So that accelerates them. And then they kind of make a collision, and they only have to lose that 10 or 20 K of thermal energy that they have, and they'll be stuck. And the acceleration they feel due to this binding of the stuff on the surface is more like 1,000 K. So they hit out of the kinetic energy sort of 1,000 K, and if they just lose 20 K of energy in that collision with the surface, they'll be bound. And so it seems to me that a high fraction will be bound of the heavy elements. Also, being heavier, these oxygens and so forth, when they hit the surface, they tend to lose more energy in the collision than lighter things, so like a hydrogen and so forth. Because I've thought a lot about it for the hydrogen. For my thesis, I had to think about the sticking probability for hydrogen, and I did this elaborate work which showed that, at high temperatures you do get bouncing, because they come in kind of fast, they just bounce off the surface. But at low temperatures, the H tended to stick, and for H was even had a weaker binding energy, and it was a lighter molecule, so it wasn't giving off as much energy when it made the collision. But even that seemed to stick fairly well. But I'll have to talk to Lou to see. I mean, did he get significantly less than 1/3 for the sticking?
I don't know the numbers, but
yeah.
I do know that it is species dependent.
Yeah.
In other words, methanol sticks better to methanol than it does to, say, methane or water.
Right. So yeah, you're right. So it may be that these two questions cancel each other. Because what you're saying is a reduction, and what Sandy's saying is that the cross-sectional area due to the ice buildup will get bigger and will increase things. And so if they're both factors of few, maybe,
And you're still home free.
I mean, yeah, the physics is so complicated that it's one of those astronomy problems where if we get kind of within a factor of 2, we're happy. Because, the original paradox was, the oxygen was supposed to have an abundance of 10 to the minus 6, and the water, and it's observed to have 10 to the minus 8, so it's a factor of 100. And where does this factor of 100 come from?
I just want to see if I understand correctly. These cases where you get complex organics because the carbon, gaseous carbon exceeds gaseous oxygen, occur only in very old clouds, like 20 million years?
Well, that would be what our theory, our theory, if our theory is right, yeah, that it should take at least a few million years before you start to get places where the carbon is greater than the oxygen, and therefore you get carbon-rich chemistry in our model. So Taurus is one of the places where I don't know if people have an age for Taurus. There's a lot of controversy about the ages of molecular clouds now, because originally they were thought to be sort of gravitationally, these giant molecular clouds were thought to be gravitationally bound, and they probably lasted for 20 million years. That was the typical figure. Recently, there's been a lot of people working in turbulence where they claim that these molecular clouds are sort of evanescent in their turbulent flows that come together and form the cloud, and then they just sort of come apart sort of at their sound speed. They just sort of, you know, come together and come apart. And they're getting shorter lifetimes, like a few million years for the cloud. And so it's hard to age a cloud. I mean, if you told me, well, is that place older than that place, it would be hard to tell, except by these chemical clocks, maybe.
Well, what fraction of clouds have these complex organics? Is it that relatively rare? Or
Rare. It's rare.
It's rare.
Yeah. It's rare, but it's, you know, it's certainly in Taurus there is. That's a good question. I should look at that.
Less than 10% or 1%?
I think so, yeah. Are there any interstellar chemists or observers who will say different? I mean, I'm not sure of that answer, but my impression, I mean, is that this place in Taurus, for example, was sort of unusual, and people were trying to figure out why is there so much carbon chemistry here. It was sort of in this unusual region, sort of.
Well, I can say something.
Yeah.
Just that everything you're saying is consistent with the fact that it's in the diffuse ISM that we found the complex hydrocarbons, like the chains of carbons and hydrogens that seem to be missing in the dense clouds. Because with Spitzer, we did a number of studies where you look at background stars through different icy clouds like this, like Whittet did. And that was the holy grail, was to try and find the diffuse hydrocarbons that would have made their way into a dense cloud, and so far they're not showing up. So I can just say it's all consistent with what you're showing.
Okay,
Yeah.
that's good.
So I know star formation isn't your field, but I was curious.
No, it is my field.
Oh, okay. Oh, okay. Okay. All right.
No,
okay,
what I'm saying is that this was my thesis, kind of was astrochemistry, and then lately I just did this oxygen problem, but mostly I'm studying star formation.
Okay, well,
and,
good.
And
then this is a good
stars.
question.
That's what I'm doing
I mean,
here.
to what do molecular clouds, as they get more chemically complex, does that aid in them cooling and collapsing?
Yes.
Because they have more molecules to
Right.
emit absorption.
Although typically the main thing that they need to form, as it turns out, is CO. That seems to be one of the dominant coolants.
Oh, so the higher organics really don't contribute.
They tend
much.
to be so low in abundance that they don't contribute to the cooling that much. If the water and the OH and some of these species had been high like we originally thought, they would have contributed to the cooling, but they're not. So
But
it
you
looks
should-
like most of the cooling, what happens is that until you get to a density of about, I don't know, 10 to the 6 or 7, the cooling is by CO, and then the gas, you start to get another cooling that comes in, which is that the grains are cold, and the gas atoms will hit a grain and it actually cools them off. They lose energy to the grain, and so gas-grain collisions can also cool at high densities.
I guess the cooler they get, the more they shield themselves from the ultraviolet light coming in too. I mean, like the center will be, or is that?
The thing that shields them, there's two things that shield them from the ultraviolet. One is the dust. You know, the more dust column you have between you and the source of UV, the less of that UV you'll see, because the dust will just absorb it. So it's a column of dust to the source that matters. And then the other thing is that sometimes they self-shield, which means that for example, suppose you're a hydrogen molecule. The hydrogen molecules that are between you and the source will absorb some of those UV photons and protect you, who is deeper in. So your fellow citizens are sort of protecting you.
So
and they do it actually, well, they get destroyed actually. So
Yeah.
they sort of lose their lives protecting you deeper in.
So the fact that you show that carbon abundance, it goes over oxygen abundance and keeps the CO high is important for cooling of molecular clouds, because if something happened to the CO, then they would last a lot longer than otherwise.
That is true. That what we're finding is that, yeah, if the grains are cold enough, well, yeah, but with time, what we find is that the carbon monoxide is destroyed and it produces this water ice, which freezes. To warm a grain up to where it releases that water into the gas, you need it to be about 100 Kelvin. And so that will eventually happen as you start to form a star. There'll be enough luminosity generated that the grains will start getting that warm, and then they liberate. In fact, this is the process that's been seen around massive stars, is that these young stars that form, they have so much luminosity that they get rid of all the ice that they have, of the grains around them, and that just dumps all this ice material into the gas, and so they see some unusual chemistries right around newly formed stars because of the liberation of all this ice.
Could that be important for planetary formation? Because if it produces this water-rich area around the star.
Well, what happens, we think, in star formation is that here we think that stars and planets form out of the dense cores of these molecular clouds, which are well shielded. And in my model, that would be all ice. Everything would be sort of ice. So that would come in. Now, if we form the sun, say, with a disk around it, some of that stuff hits the disk way out beyond Jupiter, where the dust never warms up warm enough to get rid of all the ice. So some of those dust particles actually maintain their ice, and that ice then is incorporated into comets and so forth. But if you come in closer, then you actually get warm enough that you actually lose your ice before you get to the nebula, and then you get into the disk, and the surface of the disk probably can't have too much ice for the same reason of photodesorption here, the very, very top little surface. But once you go down in the disk, it's so opaque that the ice will just reform. I mean, stuff will freeze out, and so, But there's just something called the snow line, which is right near Jupiter, which is where the radiation from the protosun heated the dust up warm enough that it was more than 100 K, and so the water ice just evaporated. But beyond this snow line, everything froze out as ice. And so it's one of the things that they think helps to form Jupiter was that there was more dust particles. They were icy. They stuck together better. There was more mass in them. It was easier to make enough of a core to create Jupiter.
Okay. Well, if you'll join me one more time in thanking Dave.
Thanks a lot.
I also have a small...
Oh, thank you.